Okay, good day to everybody, and nice to be here. And I'm going to talk about digitalization. I think we are very late on it in our industry, but it's coming, and it's going to change how we do things. So, air conditioner, refrigeration, and heat pump system, they use a lot of power, and in the current situation, the focus is really putting pressure on our industry to change. And we will see a huge increase of heat pumps on the market, and we need to make sure that these works well, but also refrigeration, air conditioning is using a lot of energy, and they are not using it in the best way they can. So it's one of the biggest power consumers in the world, and it's defining the peak loads on many markets. So we really need to work with getting them to work as they can. There is also in the grids, you can move energy, the heating energy, cooling energy, you can move the loads quite a bit. So you can offload the peaks, not only by making them efficient, but also to move it in time because of the inertia in the systems. So it's high prices is pushing this, but also, of course, the climate issues. And um, we see now that there is a huge discussion on Industry 4.0, IoT. Every unit you supply today, they have a lot of sensors in the system. The building management systems, they collect data, but it's only data. It's not used for anything. It's not analyzed in any way. So many of our large customers, they have an enormous amount of data, but it doesn't change anything. Nobody understands the data. The pressures, temperatures, powers, they are not used to anything. So this is, of course, they've done the investments in getting the data, and they want it to be used. And the industry is making money on the failures, not on efficiency. The equipment owners, they don't understand the technical things. So we have a disconnect between the desires of the equipment owners and the people servicing them. And today, people think that they have maintenance, which means that somebody come there, they might do the leak detection only, or sometimes they might tick some boxes, maybe write down some numbers, but it's extremely inefficient. If you come to a site where the system is not operating from start and you start it, you can basically not say anything on how it works because you force it to run, so it's totally out of steady state. So you don't know how it's going to work if you leave it by itself. You don't know how it worked during the night. So you need to change how this is done. This has been my baby since the mid-80s, where there was a heat pump boom in Sweden. And people buy heat pumps to save money. They buy air conditioner refrigeration to get the temperature. So if you achieve the temperature, the customers are happy. If you buy a heat pump, you do an investment, and you want to make sure that the money comes back. So then people argue if the bill doesn't decrease enough. So then they send me out with flow meters, temperature sensors, power meters. And it's basically useless tools in the field. The systems are not stable enough, the flow meters don't give you sufficient accuracy or reliability in the field, and the temperature differences are small, and the systems are unstable. So you don't get good information. So the trick is to use the thermodynamics that we learn in school in reality. So I patented the method in 1986, and then there have been products on the market since then. Then 2004, I started together with Peo to redevelop this. And today, we actually started with the cloud-based monitoring in 2007. But today, we have thousands of sites delivering data to our servers every minute. And we also have inspection tools. But of course, the future is online monitoring to a higher and higher degree. This week, we were extremely happy because of the German Energy Agency awarded us a project to build a portal for benchmarking and develop the benchmarking parameters for them. So this is a project that is going to start now, and they have realized that to get things happening in the industry, you have to push monitoring of performance, but also benchmarking. So you can compare your system with the market. So they are going to drive this by getting systems on the portal, and then you can compare that, okay, I'm below what is expected, and we will deliver all the performance analytics that we are doing on that portal. And the method is today proven. It's used all over the world. We have enormous amount of systems in supermarkets, hotels, hospitals, office buildings, Navy ships in the US, and cruise ships in the Pacific, and so on. And it's extremely simple. We just use what we learned in school. We measure pressure and temperature before the compressor, pressure and temperature after the compressor, liquid line temperature. That makes it possible to calculate the process. And then we measure, of course, evaporator inlet and outlet, condenser inlet and outlet. And the trick is that you have to realize that the energy loss is valid for a compressor as well. So forget that it is a compressor. I put energy into it. It has to come out. That makes it possible to use the compressor as a mass flow meter. Because we know the enthalpy difference, and we know the power input, so then we know the mass flow. The only error in that is the heat losses from the shell. These are small, so even a rough estimate gives you a very good value, but there is an enormous amount of experience on handling the heat losses from the shell. And if there is only the normal heat rejection from the shell, there's no forced air, no compressor cooling, it's extremely easy. If there is active cooling, we need to model that active cooling. But when we have that, we can define the whole process. And you can, in a snapshot, have all the KPIs for the compressor. The compressor isentropic efficiency, condenser condenser efficiency, evaporator efficiency, cycle efficiency, and all the conventional KPIs as approach. And when we know the cooling capacity and we know the temperature difference, we also know the mass flow of the water in a water-cooled chiller. Same on the condenser. So we have all the parameters that you could wish for in a service protocol, maintenance protocol, actually making it meaningful. And you can just click it on the bottom and have it. This is some reports that are available for those that want to learn more about the method, and they includes also uncertainty measurement and so on. It's International Energy Agency, Annex 52. They published guidelines for monitoring. It's actually, the project was focused on ground source heat pumps, and in their word, heat pumps is also cooling machines. You're pumping in heat regardless if you're interested in the cold or warm side. But this is a very useful documentation because it discusses the system boundaries and sensor accuracy, sampling intervals, and so on. And it doesn't make any difference if you are having a cooling tower or a dry cooler, or, it's valid for all. Even the focus was on ground source systems. So I showed you this, the basic circuit. There is a lot of versions, economizers. If you go to CO2 today, you have all kinds of booster systems, ejectors, parallel compressors, and so. But it's the same thermodynamics. You just need to know the process you are dealing with and calculate it correctly. And so we have all the performance data. And then, of course, when you're logging continuously, the service also build energy signatures. People talk about COP, The COP is really poor information because it varies by the minute. It's going to change from morning to evening, from this site to that site, depending on so many conditions. So most people have heard about the Carnot efficiency, which defines the idle process, and you compare with that. Typically in schools, you learn to compare with evaporation and condensing temperatures, which is kind of useless, because then you have removed all your heat exchangers. So if you then instead, if you have, for example, a water-cooled chiller, if you then look at your average temperature on the chill water and your cooling water, then you include these into your references. So then you can calculate the condenser efficiency versus indefinite condenser and indefinite flow, and the same on the evaporator. Isentropic efficiency, people have learned in school. Nobody knows what it normally is on a normal compressor. A good compressor today would have 70, 72, 74% isentropic efficiency, decreasing if you go a little bit further out on the pressure envelope. So, I mean, these are things that people should look at every time they look at on the compressor to know if the compressor is healthy or not. So, by having this information, you see a totally different perspective. Instead of having just the tip of the iceberg visual for you, you can follow the whole system. You can look at different system boundaries. You can see how efficient is my distribution system, how efficient is my heat pump or refrigeration machine. So, and these can be monitored, of course, continuously. And we need to do that. There's so many different problems that can cause inefficiency and failures. Most failures are not caused because there is a manufacturing problem in the unit. Most problems are caused by there is something provoking increased wear. And when you start looking how the system works over 24/7, over the seasons, you see that, okay, this is going to destroy this system. And these should not be left there. But nobody today has the responsibility for the operation efficiency of the site. The maintenance companies, they come once or twice a year and they check something. They have nothing to do with how it operates. The operating staff at the facilities, they have no competence to go into how efficient is this system. So we see any kinds of stupid faults. I mean, of course, there are overcharged and undercharged systems. There are compressors that are running poorly. There is filter dryers that are blocked. There is wrong flows. And the systems are getting more and more complex to reach higher and higher efficiencies. But if we don't follow up and make sure that they are actually operating okay, the complexity is going to increase the number of problems, and it's not going to improve the efficiency. We see that we basically never find a system that is efficient. There is always things to improve because nobody have looked at the systems, how they work over time. And it's not small improvements. 10 to 30% is almost all system is in that range. But many systems are even, you can halve the energy consumption. And we are not talking about replacing equipment. We're talking of making the equipment work as it is intended. And if you have this information, you can immediately see where the problem is. And you can make an alert saying that the compressor is bad, the condenser is bad, the evaporator is bad. You don't need to say that something is a problem. We see many systems like this. This is a brand new state-of-the-art CO2 systems in an ice rink. And they have a variable speed compressor. But the system is just bouncing up and down all the time. We tried to raise the interest, but nobody felt that they had the responsibility to fix it. So the contractor knew it, the manufacturer knew it, the operating staff knew it, but nobody fixed anything until they start breaking compressors. Then they fixed the control. But that costed 2 compressors. This is just another one. This is a supermarket rack. You see the evaporation temperature, the dark blue? It's fluctuating 10 degrees. Every degree is 3 to 4% of the efficiency. So it's not very good to have it fluctuating like that. This is an expansion valve fluctuating 10 degrees. It's catastrophic from energy point of view. This is a big mall in southern part of Sweden. They had a lot of problems, and we got involved and made a list of help them with identifying problems. They tried to get the contractor to fix the problems. Not very successful, so they decided to take a bigger, to go through the project by removing the influence of the chiller control and letting the external control, because there was a competent guy there to control the capacity. They reduced the energy consumption in that site to half, and they got rid of all the operating problems. So this is before and this is after. The cooling capacity, heating capacity, and then the electrical is the gray there. But you can see this is not good for energy efficiency, and it's a disaster for the screw compressors in this case. So the chiller control would start the chiller, and then it was satisfied immediately, so it turned it off. So then the oil ends up in the evaporator after some time, and the compressor wear is increased, and the oil return doesn't work. This is an example for how you catch a leak. The energy consumption start increasing, and you get an alert that you are deviating from the normal energy consumption. Some systems you have much more direct indications on leaks, but if you have a receiver, this is one of the means you can find it. So in EU you can reduce your leak checks on site if you have a monitoring system detecting effects of leaks, so indirect leak detection. You can use gas warning systems, but the gas warning system, you have to have the sensor in the perfect spot, and the leak need to be where you want it. Otherwise, you don't detect it. This is how you can see the impact of the optimization. You record baseline, you do changes, and the red is the energy consumption, and then you can see that you get a totally new pattern after the optimization. And then you can monitor that you stay there. So this was a very quick run through, and if you have any questions, I think we have 1 or 2 minutes. Otherwise, we are in this hall, booth 360, and it's 50 meters over there, so you're welcome to join us there for questions. Any direct questions now? Too many. Okay, thank you very much for listening.